Hello, so in this video I'm just going to be talking through the basics, if you like, the idea behind nonlinear programming and what we're going to effectively be looking at in this course. Right, so there's kind of the main thing that we're going to be looking at in this course is, obviously I'm going to talk a little bit about what nonlinear programming is, but basically what we're going to be looking at is how to maximize something or how to minimize something. Now that could be anything from cost to distances to most efficient way of doing things, time, for example. This literally comes up all the time in everyday life. This is a very applicable way of doing things, and it's effectively trying to find what the maximum or minimum way of doing things is. Now there is a word that is kind of linked to maximum and minimum, and this word is called efficiency. Now I'm loath to use this word as such because efficiency doesn't always mean the maximum or the minimum. Okay, so for example, you could have something that is a maximum. So let's say, for example, if you have a supermarket chain that wants to work out the most efficient way of delivering goods. So if you like, you've got supermarkets in represented by these dots, and the chain here, okay, and these are all linked by sort of roads and motorways and what have you. Yeah, okay, albeit this is a very simplified model, but hopefully you get the idea in your head. Well, the most efficient way of making a delivery may not always be the minimum way. So obviously, you would have thought, oh, it would be the minimum distance which is covered. That may not always be the case, because there may be other factors which involve, such as time, for example. So the most direct route, in other words, the route that takes the minimum distance, may not always be the most time efficient route. Obviously using motorways will be a lot quicker than using all these back routes. Okay, so, efficiency I'm kind of loath to use. I'd much prefer you to use or understand a little bit more about maximum or minimum. So that's what we're going to look at in this course. Now, there's two types of programming problems that we're going to look at. The first type that we're going to look at, and we're going to spend I'd say a little bit more than half of the course looking at, is the unconstrained problem. The unconstrained problem. So there's these things which are, and the other type, let me just write it down, the other type that we're going to look at are the constrained problems. Okay, so, we're going to spend a lot of time here, and this is just going to build up the intuition a little bit. So it's more simplified. It's more simplified, but it may not be as applicable. So, this is really actually, so we will spend a lot of time here. Right. Now, a constraint is basically a requirement that is needed. Okay, so a constraint is a requirement that's needed. So the first things first, it makes sense to start with the unconstrained problems because it's simpler. Okay, and it's slightly easier to sort of, understand and get the intuition in your head. Okay, then once we've got that intuition, you feel a little bit more comfortable and, a little bit more familiar with it. Then we're going to start looking at the constraint types. Okay, so let me just write out all the different methods that we're going to be looking at in this course. So the first type that we're going to be looking at is this thing called the one-dimensional search. Okay, then the next type that we're going to be looking at are things like quadratic forms, yeah, and hopefully you can kind of guess what that means, because the clue there being quadratic, so putting something into a quadratic form. Then we're going to look a little bit at derivatives, okay, and associated with that is Taylor series. Fairly obviously, when you want to find an approximation of a function in terms of its derivatives, it's known as the Taylor series, or you can use the Taylor series to do that. And also we're going to look then at the types of conditions that we have to impose for maximum and minimum requirements. Okay. Then we're also going to look at this thing called gradient search, right? Which basically, hopefully you can see you've got search there. So you've got a one-dimensional search here, and you've got gradient search down here. Then we're going to look at another method, which is Newton's method. So this is another search method, but we tend to call it Newton's method. And the last type for unconstrained problems is the quasi-Newton method. So it's a little bit more advanced than Newton. We kind of identify some problems in here, and we basically, correct them in here. So then let's come on to the constrained problem. So these are all the types of things that we're going to look at in the unconstrained things. Okay, then we're going to come on to the constrained problems. And the first thing which we're going to look at, well, there's two types of constraints, okay? There's first of all equality constraint. So in other words, a constraint which has an equality, basically saying that we want something equal to something else. So for example, we could have, we want a requirement that we need to make exactly three types of one product, for example. So the number of products that we have to make would be 3, so that would be an equality constraint. And coming under, and the type of method that we use for equality constraints, the Lagrange multiplier method. Now, many of you may have met that before in mathematical methods. But we'll go over it again anyway, and we'll look at it in a slightly different way. And the other type, of course, if we've got an equality constraint, so in other words, when we've got an equals sign, so an exact, if you like, then the other type would be where we can have exactly, so more than or less than, for example. And these are what's known as inequality constraints. So likewise, we can have less than something or greater than something. So we're basically saying that we need to make at least 3 types of one product. Or we have to, or for example, there might be a requirement on work staff, or the staff that make the work. So we have to basically say that we cannot make more than this amount of one product, for example. So there's many options where an inequality constraint will come in, right? And we'll talk about how, or we talked about in linear programming, how we can convert an inequalities constraint into an equality constraint by adding some what's known as slack and surplus variables. So in other words, some amount that we have to add to make it into an equality. Apologies about that. So let's talk about then. So the types of the types of things that we look at with inequality is this thing called the KKT conditions, and KKT stands for 1 minute. Karish-Kuhn-Tucker conditions, but we tend to just abbreviate it to KKT. Okay, and the last thing that we're going to look at in constrained problems, in constrained programming, is this thing called penalty methods. So in other words, if we do something, then there's a penalty which is associated with it, and so we're going to kind of look at methods that deal with that to basically make the most efficiency. So this is where efficiency very much comes in. We want the most efficient way of doing things. Well, sometimes that comes at a cost, and we look at that in this part there. So okay, what is the difference then between a linear programming problem and a non-linear programming problem? We tend to abbreviate linear programming problems as an LP, okay, and a non-linear programming problem as an NLP. Okay, and we tend to spend the majority of the time in this course. I mean, this was in another module, so we tend to spend a majority of time in this course. But what's the difference between the two? What's the difference between the two? Well, for a start, linear programming problems tend to be slightly more straightforward to deal with. Okay, there's various methods that can be used to sort out sort out linear programming problems. And again, you're probably familiar with these. I mean, you met a lot of them at A level. You met a lot of these methods at A level, which is kind of a good indication that they're not actually that tricky. They can be tricky, but they're not. They're slightly more, the ideas behind them are slightly more straightforward. Whereas these non-linear problems, non-linear programming problems, come up an awful lot more in the real world, because as you probably guessed by now, very few things in the world have a linear relationship. So in other words, as one thing changes, the other thing changes by a proportional amount, sort of a multiple. There's usually kind of other more advanced functions which are going on, and other more advanced relationships between things. So it tends to be kind of more like curves rather than a straight line. Yeah, that's the relationship between things. So what's the difference between a linear programming problem and a non-linear programming problem? Well, a linear programming problem is usually where the unit price is fixed, or the distance or whatever. It's normally where it's fixed. Okay, so in other words, it can't change. So for example, if we have two variables, x1 and x2, now these could be anything, these could be anything from products to, so this is one product and this is another product, for example. This could be one supermarket and another supermarket, for example. Yeah, they're just variables, basically. So for example, for a linear programming problem, say for example, if we're dealing with price, x1 might be £14 and x2 might be £20. Okay, so it tends to be where it's fixed. Okay, whereas with a non-linear programming problem, it's not fixed. So in other words, it varies. It varies. Okay, it varies. So that's the idea with a non-linear programming problem, and quite a lot of the time it's given in terms of the other variable. So it depends on what the other variable's doing. So for example, if you're talking in terms of price, then x1 might be given as let's stick it with price, because it doesn't really matter, it's just being made up. So let's say that x1 is given in terms of what x2 is doing. So maybe price isn't the best example, but maybe, number of units which are made. Let's say number of units which are made. X1, the number of units of x1 depend on the number of units for x2. For example, x2 might be another component which needs to be made in order to make x1. So, we need to make so many amounts of x2 in order to make x1. So, for example, this might be 7 minus 3x2. Yeah, so x1 might be given as 7 minus 3x2. So that's the idea behind non-linear and linear problem. Basically, linear problem, we tend to have fixed values. Okay, so the unit price is fixed, whereas, or the unit distance or whatever, whereas with non-linear problems, it tends to be one's given in terms of the other, or at least it varies. So it varies by some amount, right? Now, the method behind how we set up a non-linear programming problem and a linear programming problem is exactly the same. So how do we set it up? Well, the first step is always to define your variables. Okay, so define what do you have. Define variables. Okay, so, say, for example, if you have x1, so you have products, you want to define x1, x2, and so on and so on. Notice that we tend to define it sort of using the same letter. So normally you define it using, usual maths, you like define it as x1, x, y, and z, for example. Well, the trouble is with defining it like this is that we've only got a finite amount of letters. And theoretically, you could have a programming problem with hundreds of variables going on. For example, I'm thinking shipping of container ships. Okay, if you go down to the docks, you've got literally hundreds of container ships. Well, you want to define each container ship with a variable. Yeah, well, fairly obviously there's going to be more than 26. There's going to be more than 26 variables. And I say 26 because, of course, we've only got 26 letters available to us. If we don't include Greek letters or whatever, other letter alphabets. So we tend to write it like this. So we tend to say, right, okay, x is our variable. So let's say x with some subscript, so we call it xi, okay, is just basically, say, for example, container ships, okay, and this is our first container ship, this is our second container ship, and we can carry on going right through, okay. So this is why we tend to define it using this subscript notation, and we tend to always do that, right? So that's our first step. We want to define our variables. We want to look and see what we're actually working with. We want to look and see what we're actually dealing with. The second method then, or the second step, is then to define our constraints. Okay, define our constraints. So basically, are there any requirements that are needed? So another word for restraints are requirements. Okay, so basically, you need to say, are there any requirements that need to be satisfied before, for our problem? Right, and the third step is then to form the objective function. Of course, the fourth step is implied. Fourth step is then to go ahead and solve it. But this is just setting up the programming problem. So the next step then is to set up or to define what the objective function is. Okay, so in other words, do we have to, and that also includes whether we have to maximize it or whether we're looking at a minimization problem. So we're only going to be looking at either a maximize or a minimize. We want to get the most out of it or we want to get the least out of it. So for example, cost is normally to do with minimizing. So maximize or minimize basically. Okay, and the main types of objective functions. So, for example, we could be dealing with cost. So, cost is normally given by. So we'll have price per unit. Okay, we'll have price per unit. So, for example, price per unit. So, for example, we might say it costs £3 to make X1 and £4 to make X2. So, £3 for X1. So this is our first, this X1 is our first product, X2 is our second product, and it might cost £4 to make X2. Okay, but then we need to multiply it by the number of units that we make. So the number of units that we end up making, number of units. So for example, so this I always think of the objective function. I always think of the objective function as, if you like, the total. That's the thing that we want to get, that's the thing overall. So we've not broken it down, we've got to put everything together, and this is almost like the total. The objective function is almost like the total. Okay, so cost is price per unit times number of units. So let's say, for example, X1 costs £3 to make, each unit of X2 costs £4 to make, so these are price per unit, right? And let's say we make 3 units of X1 and 6 units of X2. Well, what is our total? Well, it'll be 3 lots of X1 plus... What did I say? 6 lots of X2? I can't remember exactly what I said. 3 lots of X1 we make and 6 lots of X2. So this would be our objective function. Okay, and we normally denote it by Z. And so that would obviously be, we want to minimize or maximize that. Okay, so for example. Another common example of an objective function is time. So we could have time. Similar kind of thing, similar kind of thing. We set up similar kind of way to this up here. We can also have distance. Distance is also another common one. So, like I say, distance between supermarkets. If we want to plan the most efficient route of between the supermarkets, or we want to minimise distance of supermarkets, want to minimise the distance, minimise road miles because that cuts down on petrol. So obviously the shortest distance, we normally want to minimise distance rather than maximise distance, right? So although there are of course situations where we might want to maximise distance, but minimise. We normally want to minimise distance. Well, the shortest route between 2 points. Let's say these are 2 points. Let's say this is a point x1, y1. So these are our two coordinates. It's a two-dimensional map, say, and this is x2, y2. Right, and we want to minimise the distance between those 2 points. Well, obviously the shortest distance between 2 points is given by a straight line. And of course we can define the distance of this straight line, because of course it's going to be a straight line. We can define the distance of it by using Pythagoras. So it's going to be given by the difference in the x values, so x2 minus x1 squared, plus the difference in the y values, so y2 minus y1 squared. Yeah, so that's another common example of objective functions.